All right, this is our Project Pi Encryption by Elizabeth Johnson and Julia Otten. The Vigenère cipher presented an interesting way of encrypting messages by assigning each letter a completely different letter in the alphabet. The code was not broken for many years until it was discovered that the key could be figured out by looking at the frequency of certain letters appearing. And once the key is discovered, the message can be decoded. Our encryption algorithm builds on the idea of polyalphabetic ciphers, but is much more secure than the Vigenère cipher. The idea behind our encryption algorithm is also similar to stream ciphers, but the main difference is that instead of XORing the bits of the message with their ciphertext, we instead use a form of alphabetic substitution that is highly randomized.
So the way it works is that we take our original message, hello, and we have an offset k chosen at random, and based off of that, it goes to the kth digit of pi within the first 1 billion digits of pi. Let's say it lands on the second digit, 1. Now a coin flip is done. On tails, it moves back one letter. Heads moves forward. We got tails, so we move back one letter to get G. To get the next letter, we go to the next digit of pi from our offset, which is 4. We do the coin flip and get heads, so we move forward by 4 letters from E to get I. The next digit is 1, and we flip to get heads again, so we get J. Then 5 and tails, then 9 and heads, and we have our final encrypted message from hello, GIJGX. For the decryption process, along with the encrypted message, our program generates a key file that contains the offset K, as well as a string of the sequence of heads and tails. So here is our code. The program asks the user whether they want to encrypt or decrypt their message. For the encryption process, the user types their message, and the program opens the text file for the first billion digits of pi, which is downloaded from the MIT website. The program picks a random offset, k, and makes a key from that position in pi. And it encrypts the message using the offset key and coin flips, both the size of the message. The key and coin flips are saved to a file, and the program prints the encrypted message. If the user wants to decrypt a message, they will need the encrypted message and the key file on hand. They enter the encrypted message, and the program runs the key file and basically does the encryption process in reverse. And if successful, you should see the original message that you typed. So if we run the program, and type hello, this is where I play Jeopardy music.
Right. And that will all be cut out, of course.
Of course. And here is our key and coin flips. And here is our encrypted message. The key and coin flips are saved to a file and will be used during the decryption process if needed. So if we run our program again and go to the decryption process and type our encrypted file, we should get our original message.
So to connect it to what we learned in class, we pulled some of the diagrams from when we were learning stream ciphers to make a comparison, since in many ways our algorithm is similar to the stream ciphers. So if you recall, when we were going over stream ciphers, we had these diagrams to describe the behavior of the ciphers. So this, for example, was describing when you have a key and you use the pseudo-random number generator to the length of the key, XORed with the message itself, that would give you the ciphertext for a stream cipher. So for our encryption, we also have a secret key. The key is stretched to the equal number of characters in the message. And we have our own symbol, which we have named COR, and that's our symbol for polyalphabetic substitution. So we take the key, we COR the key with the message, and that gives you the new ciphertext. We also made some equations to describe the behavior, much in the same way that we had some equations when we were going over the stream ciphers. So if you recall, we had with the stream ciphers, a message encrypted using a key K equals the message XORed with the pseudo-random number generator key in order to get the ciphertext. And then the decryption was the reverse of that process to get the message back out. So our algorithm, we ended up writing several different equations to try to describe the behavior within it. And we have a legend here to describe the various symbols and letters. So this circle with a dot is our, once again, our polyalphabetic substitution algorithm, COR. K is the offset within the digits of pi. R is the coin flips, and then H is heads and T is tails. So a message encrypted with our key is equal to the coin flips at I, CORed with the message at I. To further break it down, the coin flips at I, CORed with the message at position I, is equal to the offset plus I digit of pi. And then to kind of more deeply describe it, if the coin flips at I equals heads, then our algorithm does a Caesar shift equal to the message at I shifted to the message at the offset plus I digit of pi. And if the R sub I, if the coin flip at I equals tails, then it does a Caesar shift equal to the message at I being shifted by the message at K minus I digit of pi instead. So overall, that's essentially how our algorithm works and how we made the encryption algorithm. And thank you. Here's our references.